Hello, Assalamualaikum. So today we are going to present our group project for CSC580 parallel processing, which is sequential and MPI processing method. So this is our group member. We start off with Natra Naziha, me, Irina Atika binti Izaraimi, Muhammad Aidil Hakim, and Muhammad Irfan Shakirin. So firstly, I'm going to present about what is sequential processing. So basically, sequential processing is a computing method where all tasks are executed one after another by a single processor or a single process. The next task does not start until the current task has finished. So each task must be completed before the next task begins. Next, I'm going to present about how sequential works in the program. First, the data set size is read from the command line. Next, a single process generates the complete data set. Next, analytical tasks are executed one after another. And finally, the final results are displayed together with the execution time. So in this slide, I'm going to talk about sequential workflow. So here is the flowchart for sequential program. So firstly, the program reads the dataset size, which is n. Second, a complete synthetic dataset is generated. Next, the program execute analytical tasks sequentially. So there are 6 tasks that is needed to be executed. Firstly, basic statistic. Next, histogram generation. Next, sorting. Pearson correlation, moving average, and outlier detection. So next, the final results are displayed. Lastly, the execution time is recorded.
Okay, now I will explain the MPI method used in our project. So MPI stands for Message Passing Interface, and it is used in parallel computing to allow multiple processes to work together to complete a task. In this project, MPI is used to process the dataset using 4 processes. Each process handles the part of the data, performs its own computation, and the final result are combined at rank 0. Okay, next is how MPI works in the program. So basically, it's using 4 process how it works in our program. First is dataset size is shared using MPI underscore bcast. Second, each process generates and handles its own data chunk. Third, each process performs local computation. And fourth, a partial result are combined in rank 0. So in our MPI program, rank 0 act as the master process, as we can see from the picture. Rank 0 is responsible for displaying the final output. So the dataset size is shared to all processing using MPI broadcast. After that, each process generates and processes its own local data. Once the computation is complete, the partial result from all processes are combined using MPI function such as MPI reduce and MPI gather. So this method allows the workload to be divided among multiple processes. Okay, this slide shows the workflow of the MPI program. So we can see from the flowchart. First, the MPI program start with the MPI init. Then each process get its own rank and the total number of process using MPI com rank and MPI com size. Next, the dataset size is shared using MPI bcast, and each process then generates local data and performs local computation. After that, the partial result are combined using MPI reduce or MPI gather. Finally, rank 0 display the final result and MPI ends using MPI underscore finalize. Okay, next is MPI function used in our program. So the table show the MPI function and the purpose of the function. So first we have MPI init. So the purpose is for start the MPI environment. Second, MPI comp rank. It gets the process rank or ID. Third, MPI comp size. It's for gets the total number of processes. Next, we have MPI because it's for shares dataset size to all processes. Next is MPI reduce. It's for combine partial result from all processes. And then we have MPI double type. Is used to measure the execution time. And MPI gather for collect data from all processes to rank 0. And finally is MPI finalize. It's for ends the MPI environment.
So for this slide, I'll explain about Amdahl's law. So basically, Amdahl's law estimate the maximum performance improvement that can be achieved by parallel computing based on the portion of a program that can be parallelized. So for sequential execution, it uses a single processor. All analytical tasks are executed one after another. No parallel execution is performed. Speed up is equal to 1, which is baseline performance. For MPI parallel execution, it uses multiple MPI processes. The dataset is divided among all processes. Parallel tasks execute simultaneously, and the final results are combined using MPI communication function. So for the application of Amdahl's law in our project, for sequential, one processor execute all 6 analytical tasks and longer execution time for large data sets. For MPI, the dataset is divided using MPI scatter. Each process computes basic statistic, histogram, sorting, moving average, Pearson correlation, and outlier detection. And results are combined using MPI reduce and MPI gather.
So although MPI is designed to improve performance through parallel processing, the result in our experiment shows that MPI did not perform faster than the sequential method. This happened because MPI has additional overhead such as communication between processes, synchronization, and data gathering. Some tasks such as sorting require data to be collected back to rank 0, which increase the total execution time. So the performance of MPI depends on how the workload is divided and how communication is required between processes. So to summarize, MPI allows multiple processes to work together by dividing the workload. But in our program, four MPI processes were used to process the dataset. So based on our result, the MPI implementation took longer than the sequential implementation because of communication and synchronization overhead. This shows that parallel processing does not always guarantee for the better performance, especially when the overhead is higher than the computed computation benefit. So that's all from us. Thank you.
So now I will demonstrate the sequential processing. We are using 3 types of data: small size, medium size, and large size. In this demonstration, we will see the time it takes for each type of data to perform basic statistics, which include mean, variance, standard deviation, minimum, and the maximum. Next, we will see how long it will take for the parallel processing to generate histogram, to do sorting, Pearson correlation, moving average, and detect any outlier. So for small size data, we can see that it only took 5.3 milliseconds to perform the task and 1.8 millisecond to generate histogram. So there are 10 bins in the histogram. See how the value in the histogram are not very much different. This is because we use synthetic data. So the data it generated are uniformly distributed. So for sorting, it took 94.4 millisecond, 3.2 millisecond for Pearson correlation, and also 3.2 second for moving average. So there are 0 outlier. Again, because we use synthetic data, the data it generated do not fall too far from each other. So out all of the tasks performed in small size data, sorting is the longest task to be performed by the sequential processing. Moving on, so the time it took to perform the small size data is 108.9 millisecond. Moving on to the medium size data consisting of 10 million data, it took 51.4 millisecond to perform the basic statistics. This is 10 times longer than it took to perform the basic statistic for small size data, because the data set generated are also 10 times larger. So here we can see that sorting remain one of the longest tasks to be performed by the sequential processing. And again, no outlier detected. And the total time it took to perform the medium-sized data is 1,292 milliseconds. Okay, so if I forgot to mention, medium-sized data consists of 10 million data. So notice how it is still in millisecond measurement. So this is because we are using a quite sophisticated hardware. So the time it takes are not very much difference, only in millisecond. Compared to if we use a hardware from 10 years or 15 years back, it will take a significant amount of time to complete all these tasks. Okay, let's move on to the last data size, which is the last data size we use, which is 100 million data set. Sorry, 100 million data points. So the time it took is so much longer out of all the other two. 477.3 millisecond. And to generate the histogram, it took 163.8 millisecond. And the total time it took to complete the large data set is 14,707.7 millisecond. Okay, so that is all for the demonstration of 3 different data types, ranging from small, medium, and large. So to conclude this demonstration, we can say that if the data is larger, the time it took to complete all the tasks will take longer. That's all from me. Thank you.
Okay, so now I will continue with the explanation and demonstration of the MPI parallel implementation. Okay, so for the first test, we will use smaller data sets, which will have 1 million data sets. Okay, so here we execute the program using 4 MPI processes, and the data sets will be distributed across processes using MPI scatter. Okay, so we'll do 1 million. Okay, for each process, it performs local computation independently, so the results are combined using MPI reduce. Okay, as you can see, we've got a pretty fast output, but it is to be expected as it is just a small data set. Okay, so how will it compare to medium data sets? We will have 10 million data. Okay, so as data set sizes increase, MPI significantly reduce execution time due to parallel processing, not by comparing data using MPI. It just compares it to the sequential. So it will be significantly faster compared to sequential. Okay, so as you can see here, just under 3 seconds. Okay, so the next one is large data sets. So here we go with 100 million data. Okay, so it will take a tiny bit longer. So even with larger data sets, MPI maintains scalability by distributing workload across multiple processes. So it will be significantly faster compared to sequential. Okay, so we just wait for now. Okay, so to explain, MPI scatter is used to divide the datasets and distribute it across multiple processes. Each process computes the portion of the data independently, and MPI reduce is then used to combine all of the partial results into final global values. So, compared to the sequential execution, MPI significantly reduces execution time by distributing computation power across multiple processors. Okay, so this is the output for the larger dataset. Okay, so we observe that MPI achieve much lower execution time compared to sequential processing, especially for the larger datasets. Okay, in conclusion, this project demonstrates that MPI-based parallel programming provides significant performance improvement over sequential execution for large-scale data analytics. Okay, as proven here by these three outputs. Okay, that is all from our group, and thank you so much for your time.